All right. Hello, calculus students. Welcome to our second session in this week in AP Calculus. My name is Mr. Rich, and each week I'm going to be on here going over the topics that we studied in our AP Calculus class. Last week we started off talking about limits, and this week we are again going to be going over some basics of limits that you're going to be learning in the first unit of your AP Calculus class. So tonight, the first thing that I wanted to go over is just kind of review what are limits. I covered this last week in my live stream, but I'm going to cover it again just briefly here. So we want to talk about what are limits. Right? So that's going to be our first topic. So what I'm going to do is I'm going to share my computer screen so that you can see what I have, and we're going to start learning about limits. So let's bring up our whiteboard here. There we go. I think we got it. Let's do it. See if that holds it up. Yes, perfect. So let's talk about what are limits. This was the function that we were looking at last week. And very briefly, what is a limit? Well, I first started off that discussion by explaining what's function notation. Right? If I were to ask you on this function, what is f of 3, I'm asking you the question, when x takes on that value of 3, what is the associated y value? So we come over here to x equals 3, and we come up and we see that there's a hole, a void. So the function really does not exist at exactly x equals 3. So function notation tells us at an exact x value, what is the exact y value that's associated with that x value? In this case, there is none. If I were to pick a different number, such as 4, f of 4, you'd be able to see from this graph that when x takes on a 4 value, that the y is exactly 4. When x is exactly 4, y is exactly 4. Now, what a limit does is it allows us to express what's happening on either side of a particular x value. So instead of finding the limit as, or excuse me, the function at x equals 3, I'm going to say, what's the limit of my function f of x as x approaches 3? That's what a limit does. It's saying, okay, if you go away from 3, some infinitesimally small amount, what does the y value get close to? So the way that you could visualize this is that if you are climbing from the right-hand side and from the left-hand side here towards the x value of 3, do you converge on one particular y value? Do you get very close to a y value? And you do, right? The closer that you get to x equals 3 on either side, the closer you get to the y value of 6. So that's what we use limits for, to express not what's happening at an x value, but what's happening as you get very close to an x value on either side. So let's go into evaluating limits graphically. But the very first thing that I wanted to do is I want to talk about graphing a rational function. So one of the skills that you need to take with you from pre-calc into calculus is you should be able to take a rational function and sketch a graph of the function. That is, find out where any horizontal asymptotes or vertical asymptotes might exist, the location of any holes. You should be able to find x-intercepts, y-intercepts, okay? So what I want to do is I'm going to go ahead and go through that on an example rational function, and then evaluate some limits of that function once we have it graphed. Once we have it graphed, we can then start considering some values of limits. And then you'll see that limits really help us express behaviors of a function. So let's get into that. So I will pull back up my screen here and show you the function that I want to work with. And there it is. So I want to work with this rational function. F of x is 3x squared minus 8x minus 3 over x squared minus 9. you should have learned back in pre-calculus that if you want to sketch a graph of this, it's going to be very helpful to write each of the numerators and denominators in their factored form. So I'm going to factor x squared minus 9 as the difference of two squares. So I've got x plus 3, x minus 3. This trinomial up here, I am going to factor this. I'm going to use factoring kind of by trial and error, right? So I know that my 3x squared, when I factor this, has to be two binomials with a 3x and an x. And then I know that the factors of -3 are either -3 and 1 or 3 and -1. And so if I play around with this, I will see that putting 3x plus 1 and x minus 3, when I take my outer and inner products, right, minus 9x and a plus 1x, that's what gives me my middle term, -8x. So I'm not going to go into that any further. Do know that you should be able to factor quadratic expressions with a leading coefficient other than 1. You should be able to factor those and do that fairly quickly. So that is my rational function with my numerator and denominators completely factored. Now, what that allows me to do is it allows me, first of all, to see where my discontinuities are. So I know that I have discontinuities. I have discontinuities at x equals 3 and x equals -3, because those are the values that make my denominator here at 0. Now, for the fact that I have an x minus 3 that would cancel the x minus 3 down there, that means that the 0 that's associated with x minus 3, which is x equals 3, that's where I have a hole. So the feature that I have there is a hole, which means it's a jump, or I should say a removable discontinuity. So that's a removable discontinuity. All right, now the x equals -3, that's the 0 that's associated with the x plus 3. That means that there's a vertical asymptote there. That means that that's an infinite discontinuity. So that's an infinite discontinuity. So that means then that if I come over here to x equals -3, I know that that's going to be the location of a vertical asymptote. So I'm going to place that right there. I want to also plot the location of my hole that I have at x equals 3. So what I'm going to do is I am going to find f of 3 after I have knocked out the x minus 3s, because those would cancel each other out. That's going to give me the y value of the hole. So that's going to be a 10 on the top, 3 times 3 plus 1. So that's 10 with a 6 on the bottom. So that is going to be, what's that look like? 5/3. So about 1 2/3. So that means that my hole for this function is going to be located at 3, 1 2/3. So I'm going to plot that. So I have a hole located about there on that function. All right, the other thing that I want to plot here is my horizontal asymptote. Now, from pre-calculus, you should have learned that you can determine locations of horizontal asymptotes by examining the highest degree term in both the top and bottom of your rational function. If you have a match between the powers, the degrees on those highest degree terms, then you have a horizontal asymptote at the ratio of their coefficients. So I do have a horizontal asymptote at the location of y equals 3/1 or y equals 3. So now I have this. Now that tells me what's happening in this bottom right quadrant, that this function is coming down here, passing through the hole, and then making its way down to the vertical asymptote. Now, we do know that there is going to be an x-intercept at x equals -1/3, it looks like, because I have a x-intercept at any place my function is equal to 0, meaning right here. Whereas this, if I set that equal to 0, I'm going to get a negative 1/3. So it should be passing about there. That kind of makes sense that this thing is coming along, passing through there, and then coming down. Now that would also mean that if in terms, so that's my location of my x-intercept. I'm setting my numerator equal to 0. Now, if I want to know where the y-intercept is, I set x equal to 0. So my y-intercept is going to be at f of 0. And f of 0 is a positive 1/3. So again, that makes sense that this thing's passing through the y-axis right there, then through the x-axis at the x-axis at a negative 1/3, and then making its way to the asymptote. Now, since I don't have any other x-intercepts, that means this function really has to be doing something like this. Okay, has to be in that upper left quadrant, because if it wasn't in that upper left quadrant, there would have been another x-intercept to the left of that vertical asymptote. Now, let's just try this. Let's pick an x value of -5. Let's evaluate this function at x equals -5. I'm going to use the factored form. My numerator would be it would be a -14 on the top and a -2, which would be a +7. So that would mean, wow, by chance I just happened to nail that by accident, but that's where that thing is passing. So that kind of confirms the location of that portion of the graph that's to the left of the vertical asymptote at x equals -3. So I got a graph of this function. So notice 2 discontinuities. I've got a removable discontinuity at x equals 3. I have an infinite discontinuity or vertical asymptote at x equals -3. Now, working with this graph, let's do this. Let me see. I think I could maybe move this whole thing, capture all of that, bring it down here. Yeah. So now what I want to do is I want to now take a look at evaluating limits graphically. So we're going to take a look at this graph that we just sketched. Oh, it didn't bring down the graph with it. So let me see if I can do that. Hold on just a sec here. Okay. Let's see if I can make that work. Oh, that was at x equals -3. Yeah, that's about right. Something like that. Okay. So I'll share that with you here in just a second. So now what I want to do is we're going to take a look basically at what you learned in pre-calculus in terms of behaviors of functions. You did some what we call end behavior of functions. As x approaches infinity, what does the y value go to? It's called end behavior of functions. So we'll do that, but then I'm going to show you how that really is another way of thinking about limits, right? Limits are describing behaviors of functions. So let me show that to you. Try to make a connection between something that you knew last year in pre-calc and what you're going to be learning here in calculus with regard to limits. Okay. So what I want to do here, class, is answer a few questions about the behavior of this function. Notice that these are statements that you could have been asked in pre-calculus. For example, this says, as x approaches -infinity, the graph of f of x approaches, right? These arrows, you actually interpreted those as approaches. As x approaches -infinity, the graph of f of x approaches. Well, if we look at the graph, if I'm talking about x going to -infinity, we would be talking about this portion of the graph. We would be going out this way. And since there's a horizontal asymptote right here, and this is off just a bit, this is supposed to be at 3. See if I can get that to fall right on 3. I really can't. It's kind of in between. Okay. But we know that there's a horizontal asymptote at y equals 3, I should say, so at y equals 3. So that means that as you go further out left on the graph, that the y values are all approaching a value of 3. And then, and how we would write that as a limit is this, class. Watch, I would say that the limit of my function f of x as x approaches negative infinity is a positive 3. All right, so this is my x value, and this is the y value. Now, notice, you wouldn't want to write this. This is what we don't do. We don't say f of negative infinity is 3. That is not the way to use interval notation, or I should say function notation, because we don't put negative infinity. We put numbers in there, and that just doesn't make sense. So instead, what we do is we say, well, as x approaches negative infinity, the y values approach 3. Meaning, again, the closer that my x values get to negative infinity, the further left they go, the closer they get to 3. That's what the limit is telling us. If we then consider that as x goes to infinity, which would be out to the right, we would be on a different portion of the graph, but we would be writing out here on this. We would be following this out to positive infinity. You can see that the further that x goes out to infinity, the closer the y values get to 3. Now, one of the differences between the left-hand side here as I'm going to negative infinity and out towards positive infinity, as all of my y values as I'm going to negative infinity, the y values are above 3. Now, out to the right towards positive infinity, all those y values are below that asymptote, so they're actually all below 3. But what they have in common is they are approaching and getting closer and closer to 3. So we can write this answer as being the y values are approaching 3. So again, this limit would be written as the limit of my function f of x as x is approaching infinity is 3. All right, now let's talk about here. Let's consider this question. This says, as x approaches negative 3 from the right, from the right of negative 3 is what we mean. So if you go to x equals negative 3 and go to the right, we're talking about, since there's an asymptote there from the right, where is the function going? Let's take a look. So as we get closer to negative 3 from the right, we would be on the function heading down towards negative infinity. So the closer you get to negative 3 from the right-hand side of negative 3, the lower and lower these values are going as they approach that asymptote from the right-hand side. So the answer to that question is negative infinity. Now, how do I write this in limit notation? I would say this. I would say the limit as x approaches negative 3, and I'm going to put a superscript of plus to indicate that I'm talking about negative 3 from the right. So the limit of f of x as my x values approach negative 3 from the right is negative infinity. If we look at what's happening from the left-hand side, you can see as x approaches negative 3 from the left, the y values are going towards positive infinity. So this answer is infinity, positive infinity. Using limits, we would say the limit of my function as x approaches, this is, that's negative 3. So this is 3, okay? So let's go over here to 3. That's a different answer. As I approach 3 over here from the left, I'm getting closer and closer to the y value of the whole. Now, this graph is off a bit. We saw that that was 1 2/3 or 5/3. This y value is supposed to be, where that hole is located, is 5/3. So as you approach 3 from the left, it doesn't approach infinity, it's approaching 5/3. So we would say, as we approach 3 with a minus sign superscript. So as we approach 3 from the left-hand side of 3, the y values get very close to 5/3. Notice the function doesn't ever get to 5/3, right? Because the function doesn't exist at 3. There is a hole, a discontinuity, a removable discontinuity at 3. But the fact remains, the closer I get to x equals 3 from the left-hand side, the closer the y values are going to approach 5/3. All right, now over here, as x approaches -3 from the left-hand side, that's where the y values are going to infinity. So we would write it like this: the limit as x approaches -3 from the left, my function goes to infinity. And over here, as I approach 3, which is the location of that hole, as I approach that from the right, the graph of f of x is approaching 5/3 from the right. But we write that using limits like this. As we approach 3 from the right-hand side, the limit of f of x as x approaches 3 from the right is 5/3. All right, so that's how we use a graph, right, to evaluate limits. Now, there's going to be more to limits that I talk about next week in terms of one-sided versus two-sided limits. But I think I will cover a little bit of that here before I move on to our last topic. Now, here's the thing. There is something called the limit existence theorem. And that is that a limit is only going to exist if the limit from both the left and the right-hand side are the same value. And it has to be a value, can't be infinity. It is okay to say that a limit on the right-hand side or left-hand side of a number approaches infinity or negative infinity. But when we're talking about an overall limit, for example, if I were to say, what's the limit as x approaches -3, okay, that limit does not exist because there is no number that it gets close to. I'll go over the limit existence theorem next week, but I just want to point out that the left-hand limit at -3 is infinity, the right-hand limit is negative infinity, but since there's an asymptote there and there is no y value that the function approaches as x approaches -3, the limit doesn't exist, okay? But now, on the other hand, if I were to talk about what's the limit as x approaches 3, a positive 3, now that limit does exist because the right-hand limit right here is 5/3 as x approaches 3 from the right, and as x approaches 3 from the left, it's also 5/3. So that means the overall limit, or what we call the general limit, which is what we call a two-sided limit. These are one-sided limits from the left and from the right. The two-sided limit says, hey, the two-sided limit will exist if there is a one y value that you approach from both the left and the right. So this general limit would be a 5/3. Now, let's go to the last topic for tonight. And what that is I want us to take a look at how we would determine limits numerically. In AP Calculus, you're going to have to be doing analysis in 3 different ways. You're going to have to be doing analysis analytically, which means you'd be working with functions without the benefit of the graph of the function. You have to be able to do analysis graphically, where you maybe have a graph but don't have the actual equation or function that represents the graph. You just are working with the graph. But the third way that you're doing analysis is what we call numerically, where you're just looking at discrete values that are part of the function. So this is kind of an introduction to working numerically. So I'm probably not going to do all 4 of these tonight just for time's sake, but I'm going to do 2 of these. So let me show you what's going on here. Let's take a look at our first function. So let me share the screen back and you can see what I'm dealing with here. So what I want to do is this. I want to show you, I'm going to use the TI-84. If you've got some other graphing calculator, then for sure use that. But I'm going to pull up my TI-84 and I'm going to do a tabular numerical analysis. Now, I think the best thing for me to do, I think, is to split off my display so that you can get a better look at what I'm doing here. So here's what I'm going to do, class. I'm going to go back to my home screen. I'm going to go into my equation editor, and I'm going to put this rational equation in. So I'm going to put it in, which is x minus 2. Down in the denominator, it is 2x squared minus 9x and plus 10 down in the denominator. Now, what we're interested in doing is we're wondering what these different values are going to be in the function. So here's what I'm going to do. I'm going to go, now that I've got the function in, I'm double checking to make sure I've got it in there right. I do. If I want to evaluate the limit of my function as x approaches 2, I'm going to, I could do it graphically. I could tell my calculator to graph this function and see what's happening at 2, but I'm going to make a table of x and y values. And I'm going to tell my calculator, oh, I'll just do this. I'll do it a couple of ways. I'm going to, let me pull this back up. So what I'm going to do is call up, let's do alpha F4. There we go. So I'm going to call up my function y1 and ask it, hey, what's my function value, my y value when x is 2? And you can see that I get an error, right, because I'm dividing by 0. So apparently I have a discontinuity at 2, that this function does not exist at x equals 2. DNE stands for does not exist. That makes sense because when I put in a 2 right here in my denominator, I would have 2 times 4 minus 9 times 2 plus 10. That is a negative 8. That would be a negative 8. It'll be 8 minus 18, which is negative 10. Negative 10 plus 10 is 0. Okay, so I definitely have a 0 in my denominator, so the function is just not going to exist there. But if I want to evaluate the limit, what I want to do really is I want to take a look at what the values are on either side of 2. So I'm going to go to my table set. I'm going to tell my calculator to make an XY table of values for this function, starting at x equals 2, and I will go first in increments of 0.001. Very, very small x increments. That's what the table does, is it tells the calculator how big the jumps are to go from one x value to another. And let me try to pull up the bigger LCD screen here for you. There we go. Bring it up here. And maybe I'll shrink this down just a tad so we can get a little bit better view of what's happening here. There we go. Now, what I'm going to do is I'm going to go back to the home screen. I am now going to look at my table, and those are my x values on the left. Notice what it did. It started where I told it, x equals 2, and it went up in increments of only 0.001. So you can see that when x takes on a value of 2.001, that my y values are negative 1.002. My y value, so that's my ordered pair. You can also see when x takes on a 1.999, that it's a negative 0.998. Now, when you compare these two numbers on either side of x equals 2, you can see that we're getting very close to negative 1. So that means this limit has to be a -1 because I'm getting close to -1 on either side. Okay, so that's what is happening there. Now, what's going on at 2.01? Well, I'll go ahead and fill that table in. I'll come back up here and grab my y1, and I will change this. I'll change this to 2.01. See if I can get that to work. Let's evaluate this function at 2.01. Yeah, it's a -1.02. And then we'll do it also at 1.99 to fill in the rest of this table. There we go. All right. Hey, Alan, welcome. Glad to see you. So this would be then a -0.980. But the bottom line is, what we're really looking at is I definitely have a discontinuity at 2, but on either side of 2, like really, really close to 2, the y values are on both sides getting close to -1. So that's what my limit has to be. All right. Now, just real quick, if we were to graph this, what this means is that at x equals 2, I have, this function has a hole at -1 right there. And it would be coming in, looks like it's going to be coming in like this and going out like that, because just to the left of 2, it's under 1. Just, no, it has to be going the other way. Looks like it would be going this way. Because just to the left of x equals 2, the y values are slightly higher than -1. Okay, and then just to the right of 2, they dip below -1. So you can graph that yourself and see if that's not the behavior yet, that you have a hole at x equals 2. So that's what we call doing numerical analysis. Let's do one more of these. I'm going to do one that in our class we'll probably get to maybe in the 3rd week of class. My class would start tomorrow. It might be my first calculus classes. But let's graph this rational function, sine x over x. And what we want to do is we want to evaluate this as x approaches 0. Okay, and then what we'll do is we'll graph this in Desmos right after this, so we can confirm what our results are. So let's go into our TI-84 and let's graph this. I'll pull up this here. I'm going to go into my equation editor. Get rid of this function. I'm going to create a fraction, alpha f1. And I'm going to put sine of x, close off those parentheses, and put x. Now, one tip, right? One thing you got to know is that whenever you're using your equation editor and you're going to be graphing a trig function, you've got to be in radians mode. If not, no good. So I'm going to check to see what mode I'm in. See, I'm in degree mode. That is no good. I need to be in radian mode. Okay, so I got that fixed. Now, here's what I'm going to do. I'm going to go into my table set. I'm going to tell my TI-84 to make a table of values for this function y1, sine x over x, starting at 0 and going in increments of 0.001. And then I'm going to look at the table. So I do second function table. And you can see that the function does not exist at x equals 0. No surprise there, because when x is 0, I have a discontinuity. Makes my denominator 0. But now it's not readily apparent from your pre-calc whether that discontinuity is an asymptote or a hole. Okay, so we're going to find out here in just a second. But we do know so far that the function does not exist at 0. So if somebody said, you've got the function f of x is sine x over x, and they said, hey, what's f of 0? We know that that doesn't exist. But that doesn't tell us the behavior of the function really, really close to x equals 0. That's kind of what limits help us figure out. But if you look at what's happening here, on either side of 0, really close to 0, these y values are 1. Now, that's a rounding error right there. They're not exactly 1. They're going to be a little bit less than 1, but it's rounding up because it doesn't have enough decimals to display it. If you go far enough away from 0, you'll see things start showing up as not 1, so 0.99999. If I go back to my home screen and I evaluate my function y1 at, let's try it at negative 0.01. There you go, out to 5 decimal places, right? I mean, that's approximately 1, but it's 0.99998. And it would be the same if I did that over on the other side. It's as you'll see in just a second, that's a symmetrical function. So what's this tell us? Well, because the limit, or because the y values on either side of 0 are both getting close to a y value of 1, that's the limit. See, the function doesn't live at x equals 0. The function does not exist there. But it does tell me, the limit tells me that as I get close to 0 from both the left and the right, the y value gets really close to 1. So take a look at what this function would look like. I'm going to pull this up on Desmos, and we will take a quick look at it. See if we can bring Desmos up. Exactly, Alan, it's approaching 1, right? The limit of that function is approaching 1 as x approaches 0. You got that right. Okay, almost there. Almost there. Pulling up. And there it is. That's what I wanted. The old Desmos. See if I can get this back. There we go. All right. Let's get rid of the calculator here. Maximize that. And here we go, Alan. We are going to say we got not sock, we got sine, not sine, sine x over x. And we shall scroll out. There it is. Now, when you look at this, at what's happening at x equals 0 in Desmos, you don't notice that there's a discontinuity there. One of the, I don't know, one of the faults, I guess, of a graphing calculator, it doesn't really show you what's happening there. But if you take a look, let's just zoom way in here at x equals 0. If you run your cursor, I'm clicking and holding here, you can see that as my x values are getting closer to 0, you can see the y values are approaching 1, right? I'm at the ordered pair point x equals 0.07 and y equals 0.9992. Well, look what happens when I land right at x equals 0. If I can do it, boom, almost right there. Now you see the hole, right? There's the discontinuity. It's a removable discontinuity, x equals 0. It says 0, undefined. The function does not live at x equals 0. But because the limit is approaching 1, that tells me that, it's a removable discontinuity. Okay, so that kind of confirms our result. What our TI-84 was doing was just giving us these tabular values for x values very, very close to 0, because that's what we told it to do when we set up that table. All right, so that about does it, class. What we saw today was we looked at how we reviewed once again what are limits. We took a look at how to evaluate limits graphically. I showed you in the first part of this video how to sketch a graph of a rational function by factoring the numerator and denominator, finding your vertical asymptotes, horizontal asymptotes, your x and y intercepts, how to find the location of a hole, right? If you have a removable discontinuity, you know where it is on the x-axis, you can plug that x value into the simplified version of your rational function and find the y coordinate of that hole. And that allows you then to, make a pretty accurate sketch of the graph. Then we did that, then we determined, gee, let's find some limits of this function graphically by just looking at the graph that we had created. So we did some of that. And then actually here I'm showing you how to do it in a tabular fashion, creating X and Y ordered pairs for X values very close to the place where you're trying to find the limit. All right, so next week we'll be doing more of this and probably going a little bit more into the limit existence theorem, talking about one-sided limits versus two-sided limits, and just continuing our way through Unit 1. All right, if you are watching this on replay and you found it helpful, be sure to give the video a like, subscribe so you get notified when I am going to have a live stream or when I post any new videos. And Alan, if you're still there, I appreciate you being here, and I will see everybody next week. If you're one of my students, I'll see you in class. All right, everybody, have a great week, and I'll talk to you later.